So in a previous episode of Restoration Review number 5, or Cinco for all of you Spanish speakers in the audience, we talked about insulation, or in the steam world, the parlance is lagging. And this is the episode that I was hinting at, that we're going to be talking about the history of said lagging, or better known as insulation. So this is Trevor from History on the Move. I have 5300 here, the B&O Pacific, that's undergoing a cosmetic restoration here at the museum. And we're going to be using this as kind of our model to help us understand why we have insulation and kind of help to chronicle some of the history here. So sit back, relax, grab that favorite cup of coffee, tea, juice, whatever the heck you're drinking these days, and enjoy this episode. So to go back into the annals of steam history, we have to start off with first, the British are the first ones to have or invent the steam locomotive as a practical means of doing work. Thomas Newcomen. Now, fast forward a little bit and we get Richard Trevithick, who invents the locomotive as it is. You know, he's using a steam engine, but he's using it to propel something on rails, known as a locomotive. Now, as far back as really the beginnings of the steam engine, steam engineers and people that had worked with these things knew that an uncovered boiler or pressure vessel, and we'll use those terms interchangeably here, radiates heat outwards, okay? Think about this. If you were to boil water, right, to make tea, and who doesn't like tea? Well, some people don't, but if you were to boil water to make tea, and you have one of these, all metal stainless steel pots at your house, and you're boiling it, you can feel the heat coming off of that. If there is no form of insulation or something like a plastic layer or ceramic, something going over that stainless steel, you can feel the heat. And this is akin to what the primitive, the fathers of the steam engine were beginning to notice, that hey, we're making a fire in this thing, we're boiling water, we're making steam, but if we stand too close, we're kind of feeling a lot of this stuff. But they also knew that they were losing efficiency by doing that. Now, you and I making a cup of tea at home, doesn't really matter if we lose the efficiency. It doesn't matter, because you still get your cup of hot tea. But for a steam engine or a boiler that is doing work, you kind of need that. You kind of need something on that boiler / pressure vessel to contain all that. So the first reading I understood, or the first numbers I've seen out there, the heat loss on a stationary boiler ranged anywhere from 12 to 25% heat loss. And this was noted around 1895. Now again, there was lagging before that, but these are just numbers. We're going to get into the history of the lagging here in a minute. So they noticed, though, that the lagging helped to reduce that heat loss by roughly half, which is pretty good, because now the boiler can now generate more steam, if you will, and do it efficiently, and thereby the engine portion of the steam engine can do more work more efficiently, because that's the goal here. The British locomotives were the first ones to use lagging. And again, we'll use insulation and lagging kind of interchangeably here. So what is lagging? Well, it is something that is covering the pressure vessel itself. And it is the means to which you can contain the heat. So the British are the first ones to use the steam locomotive and the steam engine in any great quantity. And again, they invent the thing. So lagging goes back as far as 1830. And what I hold in my hand is, well, what you may see is just a piece of wood. This is a piece of pine. And pine wood, a softwood, was the first material used. Why? Well, it was readily available. Forests were still of what they call old growth lumber. Plenty of forests were all over the place, and this stuff was just plentiful by the piles. And it was a material that was also, could contain heat, not the most efficiently, but it could do the job. And the early ones used tongue and groove. And you've probably seen this in flooring before. But tongue and groove boards were used to wrap around the boiler. Now, at the museum here in Baltimore, the Lafayette, if you go into the Roundhouse, the Lafayette has this, something akin to this, pine that goes around it. And again, to contain the heat and prevent as much heat loss as possible. And some of these pine boards that were in there, they were held in place by brass hoops. And this is kind of the ways and means to keep these boards from just flying off as you're going down the track. Now, painted pine, because you don't want to just put this, because this, sitting out in the elements, will rot. So what do? They painted it. And the paint, over time, begins to wear down, and the elements are the biggest hindrance to this as a bare item on a pressure vessel. And so they're also prone to charring as steam PSI for boilers begin to increase. You get charring on the back, right? So if this is sitting facing out, the boiler vessel is here, the pressure vessel is here, and the charring, because of that intense heat, begins to occur. And again, like I said, it wood just naturally deteriorates when it's exposed to the elements. Rain, sun, heat, snow, hail, blah, 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 blah. This is where we get jacketing. And jacketing begins in the 1850s. And what is jacketing? Well, the primitive stuff is metal. Well, Russia iron was a term that was used. But it was sheet metal of sorts that was wrapped around this, right? So this is still in place along the boiler. But now, in the 1850s, you would have, like, the Memnon in the Roundhouse here at the museum also is a good example. That is a good example of very primitive jacketing. And most likely, I would fathom probably a 99% guess on this one, that Memnon had this in place as its insulation against its pressure vessel. But wood is the primary insulator, if you will, through the 19th century, or the 1800s. Now, there were a couple competing things here. Felt was one that rivaled the wood at the turn of the century, so into the early 1900s. Felt was kind of a thing that the railroads kind of caught on to. But the big thing here that people were noticing was that you're still having heat loss, and it's getting pretty, sufficient to notice. So why don't let's go back into the annals of history. One of my favorite historians, especially for railroading, is John H. White. And he was a senior historian, emeritus, at the Smithsonian Institution in District of Columbia. Long since passed, or he's passed, I think a few years ago, but the man wrote some of the most concise and just epic books about freight cars, railroad passenger cars, the early steam locomotives. Guy just wrote phenomenal stuff, and his stuff is really should be the baseline to which all of your facts should come out of. But that's just my opinion. So why don't we read some things? He actually said something in one of his books that during 1 year's service, wood shrank and charred to the point that its insulating qualities were seriously impaired, and after 4 years, it was burned out. End quote. That was literally what he said, burned out. And again, he referenced the charring on the back. Another thing that he said in this particular book is a fast-running passenger locomotive could generate enough heat to set the lagging on fire. The situation became intolerable by the 1890s, and fireproof lagging was eagerly sought. So again, John H. White did a phenomenal job on this particular book, and we'll get that later in the Cite Your Sources section. But I think this is very poignant to point out, because now, at the turn of the century, into the early 1900s, this is where the experimentation. Now, some of the stuff that we're going to talk about was already kind of being messed around with, and et cetera, but this is where the railroads really started to experiment with different types of lagging. Now, those types of material that were being experimented with were cork, so a wood semi-wood-based product, rock wool, which was, again, a mineral, and pure asbestos fibers. Now, asbestos, as everybody, mostly lawyers, will come to defense of, is it's a naturally occurring mineral in the earth. Now, I had a chance to talk to, so I work at a university, and I happen to work in one of the science departments, and I have access to geologists, and one of them is a mineralogist. And I got to pick her brain about what exactly asbestos is and how these things came about. Now, the big thing here is to point out that good quality information about this particular subject should come from reliable sources such as the USGS, or the United States Geological Survey, or peer-reviewed papers that involve this stuff. This is where the science part of this comes in. Now, so asbestos is a naturally occurring mineral, and we'll get more into that later. But I just want to kind of put that out there. That's a little, hook, line, and sinker here, and we'll come back to that subject. But that pure asbestos, as I said, was in a mattress form, so it was a lot of fibers packed into each other. But they noticed that it wasn't really doing its job as something that could tolerate heat and insulate. The pure asbestos. So, in the end of the 19th teens, so World War I, the U.S. involvement would be 1917, 1918. During that time period, roughly, depending on which sources you're looking at, what's the product known as 85% magnesia comes about. And this begins to gain popularity, especially into the 20s. The roaring 20s, if you're in the US. And 85% magnesia means just this, that 85, it's a block. It's basically a block. It's broken down like this. Now, these numbers are estimates. There are finer numbers out there, but I'm using this as an estimate. 85% of that is magnesia. There's magnesium carbonate. 9% of that was the asbestos fibers. And the asbestos fibers acted as a binding agent to hold all these other ingredients together. 4% of that was hygroscopic, or better known as water. 1% of that was lime carbonate, and the other 1%, to get you to 100, was the iron and alumina oxides. And so they mixed all these together. And again, the asbestos fibers act as a binding agent to hold all these ingredients together, because you can't just bake them and think that they're going to stay. You need something running, if you will, horizontally to hold all this stuff together. And when the railroads and the steam generation, because remember, steam is used to generate power at this time and other things. But these stationary boilers and locomotive boilers, people that are doing the tests for this stuff are noticing that this stuff is anywhere from 80 to 81% efficient at heat retention. And that's pretty epic. So that is a pretty good number, and that is why you see this stuff out on locomotives. So now we're going to talk a little bit more about everybody's favorite subject, asbestos. Well, asbestos, if you talk to a geologist, a scientist, it is a naturally occurring mineral that shows up in the earth in a fibrous type of material. That's what it is. And it's mined, and then it goes through a process to which, in the 1800s, they would strand it out. It was very, very fine. And there are two groups of it. There is the serpentine type, and this is where we get like the chrysotiles, I can never say that word, and the other type is the amphiboles. So the serpentine, there is one type, the chrysotile, and the amphiboles has 5 different types. We're not going to get into all that. That's rather unnecessary for this. You can get out there, and I'll share some sources as we get to the Cite Your Sources section. But again, a good place to start is the United States Geological Survey. Being informed about this subject can make it a little less scary and make you understand how we got to this mineral and why it became so prevalent. Now, to get into the quick history of this stuff, because, hey, we're history on the move, the Greeks and the Romans, around the different time periods, 2500 BC and 456 BC, were noted for using this stuff. It was out there already. And 775 AD, King Charlemagne of France had an asbestos tablecloth made. So I guess, you know, he was a little worried about knocking candles over. I don't know. Who knows? But King Charlemagne is on record as having a woven asbestos tablecloth. But the big push, if you will, the big push for asbestos fibers is in the 1800s. And that is known as the Industrial Revolution. So, post-Civil War in the United States, 1870s, well, that's the Reconstruction era, but we get into the end of that, into the 1880s, 1890s. This is where we get the rise of this stuff, and this is where this mineral is brought to the forefront. But it's not until we get to the 1970s and the 1980s that the health concerns for this particular fiber, mineral, really go public. Now, there were cases of this stuff, you know, causing, in some journals, they would call it the disease of the lungs or something akin to that. In the late 1800s and into the early 1900s. So it was known, but it was just not really talked about in wide circles. The thing here is that if we know a little bit more about this, it seems a little less scary. Now, it is a health concern. Let's be real, let's be honest, let's be forthright. It is a health concern. A good person to talk to about this, again, in we'll call it a practical standpoint, would be an industrial hygienist. And when I first bought my house, what was it, about 11 years ago, I had a guy who was an industrial hygienist for 40 years come into my house just to make sure things were on the up and up and, you know, there wasn't stuff here and there. But I had a really good sit-down conversation with him about asbestos fibers. And that is a person, an industrial hygienist, that you can really ask questions. And they're out there in the world. This is what these people do for a living. So I showed you the wood, right? So here's something. Now this is a piece of 85% magnesium. This is the scary stuff, okay? Now, two things to keep in mind here. This is a case. This is a plastic case. It is locked. It is locked right here. Inside of this case, there's also a membrane. It is a clear membrane, as you can see, and therefore nothing can get out. This is completely locked. So there is no dust, there is no fiber, there is nothing. That the term is friable. It is not airborne. This is completely encased, it is enclosed. This can't hurt anybody, unless you were to smash it with a hammer, but we're not gonna do that. But as you can see, this is the 85% magnesia. And you can see that it is literally, the magnesia is just a powder. So let's do a little experiment here. Let's actually go, and I'll show you what that is in just a moment. So let's get a little bit more up close with the scary stuff, as we call it. Yeah, this cannot hurt you, it can't hurt me, it can't hurt anybody. It's encapsulated in a box that is locked, that's plastic, and there is a clear membrane on both sides of the box that squeezes together. So this can't hurt you. And more importantly, it can't hurt me. So let's take a look here. So that white powdery stuff that you see, that is the magnesia carbonate. And the white, hopefully this shows up, the white fibers that you see, oh, we're going to get a bit of a glare, but if you can see the white fibers that are kind of sticking out, that is the asbestos. And again, there are three main types that are used in stuff like this. But maybe we can move this out. Yeah, so if you can kind of see I can tilt it up. You can see the fibers that are sticking out. That is the stuff that is the scary stuff. And, you know, keep in mind that, again, that this was all put together as the asbestos fibers were put in there as a binding agent. That's our most important thing here is, as it sits, this acts as a way to retain heat, keep it against the pressure vessel, and, you know, minimize the heat loss, and therefore make the work of the steam engine and the boiler the most efficient possible. So let's go down a little path here, and they're just going to be staring at my hands for a little bit here. But to understand a little bit more about magnesium carbonate, or the 85% magnesia, let's talk about that for a second. So you can actually buy magnesium carbonate. This stuff is actually given out as a dietary supplement, right? You go to your doctor, you may be prescribed this, or health stores sell it. So again, this is not this is not a health concern per se. This is, magnesium carbonate will do nothing to hurt you. And what it is, let me put that over here, it's a powder. And we'll pour some of this out for you. So you can kind of see, actually I got some of it on the table already. But this is all it is. It is just a powder like this. It's a very, very fine powder. And that's all it is. Now, I have here, not asbestos. This is actually, funny enough, my dog sheds a lot. Many of you that watch the channel for any length of time, you know I have a Carolina dog, better known as an American dingo, named Lady. Utter sweetheart. She's older than dirt. She actually turned 15 this year, so happy birthday, Lady. This is her hair, actually, is what this is. This is not asbestos. I'm just going to put that out there. This is her hair. It just kind of, you know, she sheds like you wouldn't believe. But we're going to use this as a stand-in for asbestos because, well, Lady's hair doesn't hurt anybody. And Lady's a total sweetheart. She did say I could use her hair. So what they would do is, in this process, they would take the magnesium carbonate, mix it up, and then they would take this as the essentially binding agents, right? So we could take even a little bit more. And this is kind of a rough idea as to what you're looking at in that sample I showed you. So let's grab the sample. So here's the perfectly safe, can't hurt you sample here. So bad stuff, not bad stuff, because we all love Lady. That is what this is here. So again, that stand-in here, these fibers, we'll call them, Lady's hair, is acting as a binding agent. It's bringing this magnesium carbonate together, especially when they heat it up and they turn it into the blocks. So that is, in essence, what this stuff looks like. And again, this was manufactured for long periods of time. It was used, again, into the 70s, 80s, and then the 80s is when we really get this, hey, hold up, we got a problem here. So, if you have a locomotive going down the track, doing 80, 90 miles an hour, how do you hold this 85% magnesia in place against the pressure vessel? Well, the railroads use this wire mesh, and sometimes they use a very fine wire and different bands to kind of hold this stuff against the boiler. And again, the 85% magnesia came in these blocks. You could get them in different shapes and tapers and this, that, and the other. And that is essentially how it held itself against it. And then you had the jacketing, which went on top, and that helped to hold everything in place as well. But more importantly, it kept the elements, rain, snow, sleet, hail, blah, 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 off of the lagging. Now, as we know, in the 1950s, the railroads made that big switch in the United States from steam to diesel. So as these steam locomotives are being phased out, what do we do about steam generation in the modern era, right? You know, because the steam is still being generated, it's still being used, you know, in terms of, you know, sometimes in heating capacities or electrical generation or on tourist railroads. Well, there's a material called refractory fiber. That's what this stuff is here. This is a man-made synthetic fiber. It's made by melting, and I butcher this name every time, calcined kaolin clay, or it's also made by melting alumina, silicon oxide, and other oxides, and this is the material that you get. And the neat part here is this material is good for up to 3,000 degrees Fahrenheit, whereas 85% magnesia, the range of that was roughly 600 degrees to 2,000 degrees Fahrenheit, give or take a little bit, depending on which scientific paper from the late 1800s, early 1900s that you were reading. And so this is a material. Now, tourist railroads use other things. I've seen fiberglass insulation used before and other materials. Calcium carbonate, you know, and you'd have to have some kind of fibrous synthetic material because you can't use asbestos anymore as a binding agent. So this is the quick and dirty history of insulation on steam locomotives. Why don't we go out to 5300, better known as the President Washington, to get a more hands-on look and understand the purpose of the jacketing and how the insulation fit underneath. All right, so I'm up here in the paint booth, and what we have is 5300, but more importantly. And we showed this in Restoration Review number 5 again. I'll drop a link below so you can watch that if you're interested. But as we showed prior, this is the pressure vessel itself. Maybe we can turn a light on to help you out. There's one of the rivets to it. So if you had that 85% magnesia, and again, you don't here because it's been abated, and that was back in the 60s, you would have that laying essentially where my finger is, and it would cover over this. And you would have that wire mesh like I talked about, and that will cover over that, the 85% magnesia, in order to go up and cover all that. And then your jacketing sits on top. And maybe we can get a better view up here, but yeah, I mean, it's not the best view, but you can see some of the rivets here for the boiler, the pressure vessel. But yeah, so again, to reiterate here, let's move back, that, turn that light off. So the big thing here is that the railroads need some way in order to help them to contain heat loss. Heat loss was a huge factor for steam locomotives. And the best way, and probably the most conservative by numbers and by what it took manpower wise in order to put it on and take it off, because remember, if you put on insulation when these locomotives would go into the back shops to be worked on, that has to be taken off. If it needs boiler work or whatever, locomotives like 5300 here and other steam locomotives had to have that stuff removed for when they went into these big teardown modes to check the pressure vessel, et cetera, et cetera. So you need something that can be also reused, because railroads inherently are cheap. They don't want to just buy something, use it one time, throw it away, and that's it. They want to use it again and again and again. And that was kind of the beauty of the 85% magnesia, was that so long as it didn't get damaged in use, you could reuse it. And we have to keep that in mind, that that is one of the big selling factors that these companies used with the railroads when it came to selling their insulation product to them. And something else I'll throw out there is, remember, asbestos in and of itself is, let me think how to phrase this. It is a carcinogen. That's a fact. It is also, it becomes a hazard if it becomes friable. What does that mean? Well, it becomes airborne. So those little fibers I showed you, if they break off, or you smash them into little bitty pieces, you sand it, you do whatever, and you make them airborne, and they're flying around, that's a problem. That's a problem. But if you just have the 85% magnesia sitting in place, and there's no winds blowing through or something crazy like that, there's nothing making it friable, it can't hurt you. It cannot hurt you. So long as you don't, what's the phrase? Poke the bear. Don't go poking the bear. That's bad. So leave it as it sits, right? And if you're working on a project and you do come across this stuff, have it properly abated. There are methods to do that, but you need really somebody that's licensed in your state to do that kind of stuff. And if you come to the museum here in Baltimore, you are safe. When you come into the roundhouse, there is nothing that will hurt you there. Again, things as they sit stagnant do not hurt anybody. So let's keep that in mind. That's a little disclaimer to put out there that, again, if this stuff becomes friable, that's when it becomes a health concern. So this is a section of the program that we call Cite Your Sources. Where does that come from? Well, as a former history major, I went to Towson University. That was where I did undergrad. And I had a phenomenal history professor by the name of Robert Rook. And Dr. Rook and I would sit in his office at the university, and I'd make historical discussions, and I'd say, this, that, and the other, and try to prove my point. And he'd say, well, that's great, Trevor, but you need to cite your sources. So I'd cite my sources, and we'd see if I was right. I was probably wrong most of the time. Who knows? But anyway, that is where Cite Your Sources is. That's the genesis of it. And I learned very early on from him to get out there and be very decisive in sources. So with that said, there were some really great sources I used for this particular episode talking about insulation and lagging. And one of them I referenced before was John H. White, the senior historian emeritus from the Smithsonian Institution in DC. And his book, American Locomotives and Engineering History from 1830 to 1880, is a phenomenal read. Now granted, it's got some chunk. It is not for the faint of heart, but it is concise, It is very well done. It's scholarly, and there is some really good information about the beginnings of lagging and insulation before we get to the 85% magnesia stuff. So, can't recommend that one enough. Another one that I found super helpful was the, you can't really see it, but the Locomotive Catechism by a guy named Grimshaw. What was his name? Robert Grimshaw, mechanical engineer. Really gets into all the stuff you ever want to know about locomotives, but he has a great section in there. And a lot of these books from the 1880s, 1890s, early 1900s had question and answer sections, and I found that one to be super helpful in talking about the early 1900s and the testing of, you know, the 85% magnesia and, you know, rock wool versus this, that, and the other. So very helpful guide. Now, if you want to learn more about the 85% magnesia that we talked about, there is literally a manual for it. Yeah, this guy here. I own this one. This is kind of neat. So this came from the Magnesia Insulation Manufacturers Association. Copyright is 1949, so clearly this was in the very peak of when this stuff was being used. They have some good information in here, tables, technical terms, where, you know, where this stuff would have been applied, you know, the makeup of it, etc., etc. Great photos, like you can actually see them here putting the stuff onto a boiler or pressure vessel. So again, this was super helpful. Kind of hard to find though. Another good one is catalogs of asbestos manufacturers from back in the day. The condensed catalog of Cary, asbestos, and magnesia products. I've had this one for a little while. This was 1932. This is again a primary source. This came right from the time period. And there is some really good stuff in here, excuse me. There's some really good stuff in here about how, it also talked about how the fibers were put into things like cement and wallboard and all kinds of other products, not just the 85% magnesia. Something else I found super helpful is the Google Books, because if you go looking and be decisive in your sources, you can find stuff like this. This is Loco, a technical magazine from 1912. And they had a really good article in here called Boiler Coverings. I found this one to be very helpful. There were a lot of good stuff. And I mean, there's piles of these things out there. You can just get on Google Books and look for this stuff. But again, be decisive in the sources. And I highly recommend that you go out and please buy your sources. Don't go stealing books. And if you borrow them from somebody, please give them back. Like, nobody likes books that just go bop, 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 and they walk away and they never come home. And then your heart hurts forever. Nah, that's no good. So please return your books. And I'm not here to peddle and to tell you, you know, where to buy this stuff, but just buy them, you know, from a reputable dealer. But, you know, get out there, be decisive in the sources that you read. Wow, we really covered a lot of ground here in terms of understanding insulation, or better known as lagging. We've got a good history of it from the genesis, the beginning of it, to basically the end of the steam era. And, you know, there's a lot of ground here that we covered in between, and some really good information out there. And when it comes to the scary stuff, as I call it, get out there and do your homework, right? I will drop some of the links below that I used. Remember, geologists are your friend in this case. They have a swath of information about a naturally occurring mineral known as asbestos. And there is some good information out there on government websites and peer-reviewed websites and places like that for you to read and make yourself informed, because that is what's most important. Being informed and understanding this stuff makes it a little less scary. Doesn't mean you shouldn't take precautions. You should. But it makes it a little less scary. And an informed person is an understanding person, and you can make good decisions. So this is Trevor from History on the Move. Get out there. I want you to read history, explore history, but most importantly, I want you to make your own history. I'll see you on the next one.